will discuss about the speed control of DC motors. So whenever we are discussing about the speed control of DC motors, there are two types generally. One is the DC shunt motor, another is the DC series motor. So for these two types of motor, there are different methods for controlling the speed. So generally the back EMF equation is being given by EB is equal to P phi Z N by 60A. So P is the number of poles, phi is the flux per pole, Z is the number of conductors, N is the speed in RPM, then A, that is the number of parallel paths. So in DC motors, generally the number of poles is being fixed, that is being decided by the manufacturers. Similarly, the total number of conductors will also remain fixed. Number of parallel paths will also remain fixed. So only variable is that phi and n. So we can say EB is directly proportional to phi n. So n is directly proportional to EB by phi. Hence, speed is directly proportional to the back EMF of the motor and speed is inversely proportional to the flux. So with these two variables, we can define the two different methods for controlling the speed of the DC shunt motors. So for controlling the flux, we can use the flux control method. So first we will discuss about the flux control method. So this is flux control method. So in flux control method, we will have to vary the flux in the field. So to vary the flux, we will have to control the field current. So in DC shunt motors, normally this is the field circuit. With that, we will have to insert the variable resistance. This is your armature. So here the voltage is being supply voltage is being given, DC supply voltage is being given here. Due to that, the total current I will flow through this. Armature current IA, here the field current ISH will be given, and the field resistance will be given as RSH. This R is the external resistance which will be included in the field circuit. So whenever we vary this field circuit, we know that the field current is given as ISH is equal to V by RSH plus R, because this is the total resistance. RSH plus R is the total resistance of the field circuit. So RSH means that is the field coil resistance, and R is the resistance of the external circuit which is being included in the field circuit. So by varying this R, we can vary the ISH. So now if we will increase this R automatically, because the minimum value of R is 0. So whenever we will give the minimum value of R, in that case V by RSH will be the maximum. So in that case, the current will be maximum, and we know that flux is directly proportional to ISH. So therefore, if the current will be maximum, the flux will be maximum. And when the flux will be maximum, speed we know that N is directly proportional to 1 by phi. So therefore, when the phi will be maximum, speed will be minimum. So therefore, by inserting the external resistance here, we can reduce the current, field current. So whenever the field current will be reduced, automatically the flux will get reduced. So when the flux will get reduced, the speed will get increased. So in this case, the speed can be increased only. But there is some limitations are also there. Whenever we are increasing the speed, that is by decreasing the flux. So the flux can be reduced to a certain minimum value. Because if we reduce the flux beyond the minimum value, then the voltage build-up in the field circuit may not be possible. So therefore, the flux can be minimized or can be reduced to a certain value. Therefore, the speed can be increased to a certain value. So therefore, there will be a maximum limit for the increase in speed. So therefore, in flux control method, the speed can be increased only. So you can say N can be increased only. So for increasing the speed of a DC shunt motor, we can use the flux control method. So next one is how to reduce the speed. So to reduce the speed, we can use another method that is known as armature voltage control method. So now we will discuss about the armature voltage control method. So this is armature voltage control method. That means we know that the speed is directly proportional to EB when phi remains constant, because there are two variables. One is the back EMF, another is the flux. So whenever we are varying this EB, that means we will have to keep the flux constant. So to keep the flux constant means the field current should remain constant. And as we know that field current is directly proportional to the supply voltage. So therefore, until the supply voltage remains constant, the field current will also remain constant. Here we are assuming that the supply voltage remains constant always. So therefore, the field current remains constant and hence the flux also remains constant. So now, here EB is equal to V minus IR. So RA, this is the resistance of the armature circuit, and IARA, this is the voltage drop in armature circuit. So if we increase this voltage drop, then automatically the speed will be decreased, because if we increase IARA, V minus IARA will decrease. So if this part will decrease, automatically the speed will be decreased here. So therefore, for that circuit, you can draw so here it is the sun motor with supply voltage V, DC supply voltage. Due to that, the total current, supply current I will flow through this, and this is the armature current which is flowing through the armature, and here it is ISH. RSH remains fixed. If RSH remains fixed, automatically ISH will remains constant. So this is the external resistance which will be included in series with the armature. Now the armature resistance here it is RA. So therefore, the total resistance across the armature circuit will be R plus RA. So the voltage drop in the armature circuit will be given as, now you can say EB is equals to V minus IA into R plus RA. So this R is the external circuit resistance which is included in series with the armature circuit. So now by increasing this R, that is the external resistance, if we will increase this, the voltage drop here will increase. So if the voltage drop will increase, EB will decrease. So when EB will decrease, you know that speed is directly proportional to EB. So when the EB will decrease, the speed will decrease. So therefore, in this method or in this speed control method, we can reduce the speed of the DC shunt motor. So therefore, we can say N is directly proportional to here, or you can say is equal to, directly proportional to V minus IA into R plus RA. So here the speed can be decreased only. But here also one limitations are there, because whenever we are decreasing the speed, if the speed will be decreased beyond the critical value, then also it will not be possible to run the motor. So therefore, in case of the flux control method, the speed can be increased, but there is some limitations. The speed cannot be increased beyond certain value. Similarly, here also the speed can be, in case of the armature voltage control, the speed can be decreased only. So here also some limitations are there. Speed cannot be decreased beyond the critical value. So these are the two methods which are being used in case of the DC shunt motors. So similarly, there are some methods of speed control in case of the DC series motors. So in DC series motors, we can use different methods. That is, so this is speed control of DC series motor. So in DC series motor, the total current that is line current, we can say. The total line current is flowing through the field circuit. So now here the supply voltage is V here, and the same current will flow through the field circuit as well as the armature circuit. So now to change the flux in the field control, simply we are saying the field control method, this is also. So to control the speed, we will have to control or we will have to change the current through the field circuit. So to change the current through the field circuit, we can use a field diverter. So here it is the field diverter. So field diverter means it will divert certain current through this external resistance so that the current through the field winding will get reduced. And that can be set by according to what magnitude of speed will be desired. So if we want to decrease the speed to a certain value, then we can bypass the certain current here. So that is known as the this is known as the field diverter method. That means we are diverting the field current through an external resistance to reduce the current through the field circuit. So if the field means flux will get reduced, we know that N is directly proportional to 1 by phi, and we know that phi is directly proportional to ISH. So now if certain amount of current will get diverted through this external resistance, the current through the field circuit will get reduced. So if the current through the field circuit will get reduced, the flux through the field current will also get reduced. The flux produced by the field will get reduced. So if the flux through the field will get reduced, then automatically the speed will get increased. So in this method we can increase the speed of the DC series motor. So this is one method. Then another method is that tapped field control. So that is known as tapped field control. So tapped field control means we will have to bring some tappings from the field circuit. So that means this is your armature. Then the field circuit will be given like this. So tappings will be taken out here. The supply will be given. So now see, by bringing out the tappings in the field circuit, we can divide the field circuit into certain sections. So now, whenever this tapping, this pointer will be in contact with some taps, then a certain portion of the fields will be included in the armature. So in that case, as we can reduce or we can increase the field resistance. So field resistance will get changed means we know that what is the current which is being flowing through this, I will be equal to V divided by RA plus RSH. So in this method we are varying the RSH by varying the length of the field coils. So when the length of the field coils will get varied, means will get decreased, RSH will get decreased. So if the RSH will get decreased, automatically the current will increase. So if the current will increase, then automatically the flux will increase. So if the flux will increase, then speed will get also reduced. So in this method also, the speed can be reduced by using the tapped field control. So the name suggests itself, the tapped field control. That means from the field circuit we are bringing out some tappings. By that we are varying the field resistance, and by varying the field resistance we are varying the flux through the flux produced in the field circuit, and thereby we are changing the speed of the DC series motor. So that is tapped field control method. So another method is there, that is parallel field control method. So this is parallel field control method. So in this, what we are doing exactly, we can arrange the field circuit some different sections of field circuit in different manner. Means either you can connect them in series or you can connect them in parallel. So if we connect them in series, this is the supply voltage. So now these are the different parts of the field circuit. So number of field circuits will be there and they will be connected. If we want 2 field circuits or 3 field circuits like that. So according to the design, we can change the speed of the motor, and this is basically we are not changing the speed of the motor here, but we are designing for specific speeds. Similarly, this is a series method. Similarly, we can arrange this field circuit in parallel. So this is parallel method actually. Means these 2 field circuits are connected in parallel. In the previous case, we have connected the field circuits in series, but here we are connecting them in parallel. So whenever we are connecting them in series, automatically the field resistance will get increased. So due to the increase in field resistance, the current through the field circuits will get reduced. So due to the reduction in the field circuit, the flux will get reduced, and due to the reduction in the flux, the speed will be increased. Similarly here, whenever we are connecting the field circuits in parallel, the field resistance will get reduced. So if the field resistance will get reduced, the current from the field circuit will get increased. So automatically, the both will produce certain amount of flux. In that case, the flux will be increased and the speed can be decreased. Similarly, along with that, we can also arrange in a different way, an external resistance can be connected in parallel with this, and that is a variable resistance. So if we connect an external resistance in parallel with these field circuits, and by varying this external resistance, we can vary the current for the field circuit. Because whatever the current will be drawn, that depends on the load. So the load current will remain fixed, but the current for the field circuit will only be varied. So by varying the field current for the field circuit, the flux can be varied, and along with the varying flux, the speed of the DC series motor can also be varied. So these are the different ways by which we can change the speed of either DC series motor or DC shunt motors. So this is all about your speed control of DC motor. Thank you all.